Good morning, everybody.
Good morning.
Let's get started. Okay, so what we're going to be doing today, we're going to be finishing the filter realization. And hopefully, after we finish the filter realization, we're going to start the frequency analysis. Okay, so in the previous class we looked at different ways of realizing the filter, and we said we can manipulate the transfer function of the filter, and therefore we are able to realize the filter using different structures. So we looked at the direct form 1, we looked at the direct form 2, and that's all what we looked at. And direct form 2 for the IR filters. Now we realize with different realization, there are different delay elements that we have to use. And there are also different number of multiplications and additions that the realization will entail. Now we're going to do at the end an example to show the rounding impact on the filter realization. So in theory, everything is ideal and we have infinite number of bits to represent the numbers, then all of the filter realization are equal. However, if you're concerned about memories, if you're concerned about the rounding, the quantization, then different realization will provide different accuracy. Okay, so we're going to continue with the filter realization. We're going to finish the IR filters and then we're going to move to the FIR filters. And again, we'll do an example that shows the impact of the quantization on the filter realization accuracy. So the next form that we can use to realize the filter is the cascade form. And the idea behind the cascade form is that we're going to break h of z into the product of second order forms, and we're going to use the direct form 2 for each of the section. So therefore, we're going to take h of z, and we're going to write h of z as a constant multiplied by, this is the multiplication, or the product, from 1 to k, 1 plus b1i z to negative 1, plus b2i z to negative 2, divided by 1 plus alpha 1i z to negative 1, plus alpha 2i z to negative 2. And apparently, since we are making the product of k, the filter order, or the total order of the filter, n, is equal to 2 multiplied by k. Since this is squared, or second order, and we're multiplying them k times. Okay. So how does this filter with the cascade realization look like? We're going to take B0, and then we're going to take a delay, and then we're going to have beta, or B11, and we're going to have negative alpha 1, 1, negative alpha 2, 1, And you add them together. And the second block is going to look very similar to the first one. Okay. So the same thing, B1, B11, although this is B1I, sorry, this is B1I, B2I, alpha 1I, alpha 2I, all the way to B1K, B2K, and then added them together. And this is negative alpha 1K, negative alpha 2K, and so on, all the way to generate Y of n.
So each one of those is a division?
Each one of these are division? No?
I just don't really understand how the numerator and the denominator.
Well, this one is from the direct form too. If we take just this one,
Yep.
this is no different than what we've done with the direct form 2, which is here. A second order. So we're just having to use these.
Okay.
Make sense? Why?
It's fine. I'll just go back and watch that later. I just forget.
Okay, so but nevertheless, in the direct form 2, where we have this form, we can realize the filter using, if it's a second order, 2 delay elements. And these are the B's, these are the alphas. So that one, we broke it down into the product of a second order forms. So each one of these is a direct form 2. Direct form 2, multiplied by each other. Again, this form, this block here, if it is a second order, is the same as this one. Except for P0 is a 1 in the second case. So this shape from the direct form 2 is the shape we're using for the cascade. Good? Any other questions? Okay, so looking at this form, each section is going to have 4 multiplications and each section is going to have 2 delays in general. Now also, if we have a first order section, so here, if the order of the filter is odd, we're going to have second order multiplied by second order multiplied by second order, then we're going to have one that is going to be an odd order. So if it is an odd, we can use it with B2i and alpha 2i equal to a 0. Does that make sense? Mm-hmm. So we can take the product. If I set this to a 0, this to a 0, this becomes the first order, which is P2 0, alpha 2 equal to a 0. So, therefore, if n is odd, then at least one section is going to be of first order. Okay. Finally, the next form that we can have is the parallel form. And in here we're going to break h of z into partial fraction, first and second order, and combine the smaller forms as parallel direct 2 forms.
Should there be an L at the end of parallel?
Yes, thanks. So we're going to break h of z into partial fraction expansion that are first and second order. And we're going to combine smaller forms as parallel direct 2 forms. Okay. So given h of z, we're going to write h of z as gamma 0 plus the summation from I equal 1 to k, gamma 0I plus gamma 1I, z to negative 1 divided by 1 plus alpha 1I, z to negative 1 plus alpha 2, I z to negative 2. So this, if we expanding the h of z as a second order, or we can have the summation from I equal 1 to 2k ai divided by 1 minus pi multiplied by zi, multiplied by z to negative 1. Either one. So this or the other one. So in the cascade, we multiply all these terms together. And here, we're adding all these terms together. So therefore, and again here also the further order n is equal to 2 multiplied by k. Since each one is squared and it is to the k, it's going to be k multiplied by 2. Okay, so this filter realization is going to look something like this. You're going to have gamma 0 and then we're going to have the realization using direct form, gamma 0 1 added z to negative 1, gamma 1 1 and then we have negative alpha 1 1 is added z to negative 1, negative alpha 2 1, and we're going to add these together. Again, this comes from the direct form 2. Okay, so this is one of them, but we're going to have up to k of them. So we're going to have multiple of these all the way to the last one, which is going to look something like this. Gamma 0k gamma 1k, negative alpha 1k, negative alpha 2k. We're going to add these together. And we're going to add this to this, and we're going to add all these together to generate y of n. Okay. So again, each one of these is a direct second form, or direct form Q. Okay, so each section is going to have 4 multiplications and 2 delay elements. And of course, if we have a first order system, then alpha 1, 1 and alpha 1, 2 is going to equal to a 0. Sorry, gamma, we have a first order system. I mean, comparing these forms, this term is going to be equal to a 0, and this term is going to be equal to a 0 to match this form. Does that make sense? Everybody? So this for first order gamma 1i is going to equal to alpha 2i, which is going to equal to a 0. And gamma 0i is going to equal to ai. And alpha 1i is going to equal to negative pi. Okay. Okay, let's do an example of an actual transfer function and look at different realization of it.
Real quick, can we see the bottom of that diagram?
Mm-hmm. It's going to be similar to this one.
Will it have a final time delay between the
There
bottom?
is a time delay that's missing in there,
When you make-
unintentionally. Good
I just
catch.
wanted to make sure of that, because I noticed that.
Yeah. And this multiplication is meant to be here. You good? Okay, so let's look at an example with all these different realization of the IIR filter. So if we have h of z that is equal to a 10, multiplied by 1 plus 5 over 6 z to negative 1 minus 2 z to negative 2 plus 2 over 3 z to negative 3 divided by 1 minus 15 divided by 8 z to negative 1 plus 47 over 32 z to negative 2 minus 17 over 32 z to negative 3 plus 3 over 64 z to negative 4. So we're going to look at the direct form 2, the cascade form, and then the parallel form. So the first form is the direct form 2. We're going to have x of n, and we can use the signal flow to represent this, so it's easier to plot. So in this form, if you remember, this is this form, where we have an intermediate variable that's w of n, and this will have the numerators coefficients, the denominator coefficients. So we're going to have a 1. This is going to be w of n. This is going to be a 10. Then we're going to have a delay that we represent by z to negative 1. Then we're going to have multiplication. What should go in here? 50 over 6. It's the numerator. 50 over 6. And then we're going to have another delay. And then we're going to have negative 20.
It doesn't matter which side, you can, right? It's a year, right, of each?
No, it will matter. Verify it does not matter and let me know. Okay. But this was derived mathematically. And mathematically, I mean, when we...
Oh, yeah, you're adding on there, okay.
Yeah.
Yes,
Scroll up real quick. Yes.
Yeah.
Not your time.
20 over 3, and then we're going to add all these together. And we're going to take 15 over 8, negative 47 over 32, negative 17 over 32, and we're going to need one more. This is z to negative 1, that is negative 3 over 64, and then we're going to add all these together.
Should it be plus 47 over 32? And negative?
No, this will be the negative of these coefficients. These coefficients are the negative of the denominator coefficients.
Okay. But not
So we have here, they are the same sign. Here, they will be the negative of them. So negative 15 will be 15. 47 over 32, negative 47 over 32, and so on. And again, this comes directly from that derivation. So here, twin, we multiply it by a negative sign, the coefficients. Okay. So this is the direct to realization. The number of multiplications is equal to 1, 2, 3, 4, 5, 6, 7, and 1 is 8. and number of delay elements are equal to a 4. 4 multiplications, 4 and 4, 4 and 4, and 4 delays. Okay. Okay, the second form is the cascade form. See if it's going to fit in here. Mm-hmm.
I just was a note about the number multiplication. So the right-hand side only has the 3, right?
Has 4. There's a 10 here.
Okay.
I wrote the 10 far away, so it ends.
So, but wouldn't you count the 1 too? So wouldn't it be?
I mean, you could. I mean, in general,
Okay,
these are
okay.
very right number, but this one is usually normalized by this one.
Okay.
Okay. The cascade form, we need to find the roots. And therefore, we're going to write h of z as equal to a 10 multiplied by 1 minus 1/2 z to negative 1 multiplied by 1 minus 2 over 3 z to negative 1 multiplied by 1 plus 2 z to negative 1 divided by 1 minus 3 over 4 z to negative 1 multiplies by 1 minus 1 over 8 z to negative 1 1 minus 1/2 plus j 1/2 z to negative 1 1 minus 1/2 minus j 1/2 z to negative 1. So apparently I could multiply here z to the 4, and then it will be z minus 3 over 4, z minus 1 over 8, or in this form. Both of them, I mean, this form should be able to do it with a positive z, but we have it in a form where we have the negatives of the z's. Okay, so looking at this form, we have 3 real zeros, and we have 2 real poles, and we have 2 complex conjugate poles. Okay. So we can expand this as 2 first order or 2 second order system. And what we're going to do is we're going to combine the real poles into a second 2 first order system or 1 second order system. And the complex conjugates, we have 2 complex conjugate poles. We're going to implement them using 1 second order section. Okay. So therefore, we're going to write h of z as the following. We're going to write it as 10 multiplied by 1 minus 2 over 3 z to negative 1 divided by 1 minus 7 over 8 z to negative 1 plus 3 over 32 z to negative 2 multiplied by 1 plus 3 over 2 z to negative 1 minus z to negative 2 divided by 1 minus z to negative 1 plus 1/2 z to negative 2. Does anybody know what we've done?
I mean,
what is it? We combine these two into this. We combined these two into this, and we combined these two into this.
Okay, so then should,
So this will give me second order. This is the first order. This is the second order. This is the second order. Together? Is that clear? Everybody?
use that, wouldn't it be 1 minus 1/2, not 2/3?
No, sorry. This one and that one. I labeled it wrong. Very good. So this one is this one, and this one is this one. Good catch. Okay, so we can what are the equals of this polynomial? Anybody want to guess? One half plus minus 1/2. It's coming directly from here. Okay. So therefore, we can have the cascade form. Okay. So this is a 10. This is x of n. This is 7/8. And this is -3/32. This is 1. This is minus 1/2. This is a 3/2. And this is a -1. And this is our y of n. Assuming I did not miss anything. Okay.
For the first 3 blocks, for the one on the right, wouldn't there be a negative 2/3?
Which one?
For the block first,
3/2 and 1.
for the first group of blocks.
This
the
one?
Yeah, the one on the right.
There is a number missing. -1. This is 1 and -2/3. Okay, very good. So looking at the number of multiplications, we have 6 multiplications. And number of the Lie elements equal to a 4. Okay. Finally, we're going to look at the parallel form. So we're going to do partial fraction expansion. And if the numerator is greater than or equal the numerator order, then we're going to divide and have a quotient. Okay, so in this case we have h of z. The numerator is less than the denominator, so we're going to expand h of z as equal to a1 divided by 1 minus 3 over 4 z to negative 1 plus a2 1 minus 1 over 8 z to negative 1 plus a3 plus a4 z to negative 1 divided by 1 minus z to negative 1 plus 1/2 z to negative 2. Together? Everybody? So looking here at h of z, we expanded this term. Since these are complex roots, we just combine, we fit them together. We're going to expand it as a second order term. Okay, so a1, the residues, a1 is going to equal to 2.93, a2 equal to negative 17.68, and a3 is going to equal to 24.75, and a4 is going to equal to 2.345. So therefore,
And I'm sorry, what was the first one?
Yeah.
A1?
2.9, which one?
Thank you.
2.93. Okay, so this is the 2.93, negative 17.68, and this is 2.24.75 and 2.345. Now we're going to also combine these together. And these combined are going to be negative 14.75 plus 12.9 z to negative 1 divided by 1 minus 7 over 8 z to negative 1 plus 3 over 32 z to negative 2. Because we could have kept it each one alone. And we can also combine them together. Okay. So again, each one of these is going to be using direct form 2. You have something that looks like this. This is x of n. Okay. This is y of n. This is 1. This is negative 14.75. This is 12.9. This is z negative 1. Z negative 1. Negative 3 over 32. 7 over 8. And from the second term, we have 24.75, 2.34, z negative 1, z negative 1, and we have a 1 and minus 1/2. Okay. So looking at the number of multiplications, 1, 2, 3, 4, 1, 1, 2, 3, 4, 2, 3. How many multiplications we're going to have? 2, 2, 2, 2, 4. And number of delay elements is equal to a 4. Of course, in this particular case, this is just a 1, so there's no multiplication. But in general, this might not be a 1. Okay. Any questions? Is it a little bit dull topic?
If we look at the original Cascade example,
The cascade?
yeah, Cascade.
Well, 6 multipliers, 4 delays.
Yeah. 1 delay, 2, 3, 4.
Thank you.
You're welcome. Okay.
So does that mean we would pick Cascade as the best one since it requires the least elements?
I mean, as we're going to see, there are multiple considerations when you look at the realization. The number of multiplication, number of delays, and the impact of rounding and quantization on the filter performance. Together? So we'll do an example that will look just at the quantization, and we'll see how two different realization will perform differently. Okay. So before we do that, though, we're going to finish, we're going to look at the FIR filter realization. And luckily, the FIR filter realization is much simpler. So hopefully we'll be able to finish all this topic today. Okay, so if we have an FIR filter, H of Z is going to equal the summation from k equals 0 to n minus 1, bk, z to negative k, where this bk is nothing other than h of k, the coefficient of h of n, or the kth coefficient of h of n. Okay. Actually, let's just write it as h of k, which is equal the summation from k equals 0 to n minus 1, bk, z to negative k. And this assumes that h of k is equal to bk when k is between 0 and less than n minus 1 and 0 elsewhere. Okay, so the first form we're going to look at is the direct form. And in this form, See how neat the structure is? We're going to have x of n. We're going to have a delay z to negative 1. We're going to have h of 0. Then we're going to have h of 1, a delay, a delay, a delay, a delay, a delay. And this will be y of n. H of n minus 1. And probably I should have also wrote the expression for the convolution. So I'm going to just slide this down. So if you look at the output of the filter, y of n is going to equal the summation from k equals 0 to n minus 1, h of k multiplied by x of n minus k, which is the convolution of the impulse response of the filter with x of n. So it's going to equal h of 0 multiplied by x of n, h of 1, x of n minus 1, h of 2, x of n minus 2, and so on and so forth. Together? Okay. So if you look at this filter, this looks similar to the direct form 2 with all the a's equal to a 0. So with the filter not having a denominator, the denominator is equal to a 1 here.
There's no poles.
There is no poles, yes. Equal with no poles. Okay, so therefore the number of multiplication is equal to n, and number of delay elements is going to equal to n minus 1. Okay. The next form is the cascade form. And for this form, we're going to write or rewrite h of z as a product of a second order factors. So therefore, h of z, we can write it as b0 multiplied by the product from k equal 1 to n over 2. And we'll see what this sign means. b1k, z to negative 1, plus b2k, z to negative 2. And m is equal to n over 2. Means the largest integer less than or equal to n over 2. Okay. So if you look at this form, we have x of n, b0, y of n, and we're going to have a delay b11, add it together, b to 1, z to negative 1, z to negative 1, and the same form is going to repeat. Is that clear? Makes sense? How many multiplications we have? We have each in each branch, and we have m of these branches. So we have 2m. And how many delay elements? It's also going to equal 2 multiplied by m. Okay. Because this looks similar to the IIR cascade filter with all the a's equal to a 0. Again, because it doesn't have a denominator. Okay. Finally, the last structure we're going to look at is the structure of the FIR filter that has a linear phase.
So we can't do a parallel.
What is the condition for the linear phase of the FIR filter? Anybody remembers on top of their head?
On top of the head.
Okay, we have to have a symmetry,
All right.
whether an odd or even symmetry. You can forget everything you want to forget about FIR filters. One thing you should not forget is that if there is a symmetry, there is a linear phase. Okay, so using this symmetry, we can show that y of n can be written as the summation from k equals 0 to n minus 1 h of k x of n minus k. This is the convolution. We can show that it can be written as the following. Either y of n equal the summation from k equals 0 to n minus 3 let's give it some space. Y of n equal the summation from k equals 0 to n minus 3 divided by 2 h of k multiplied by x of n minus k plus x of n minus 1 plus k plus h of n minus 1 over 2 x of n minus 1 over 2 So what we can do using the symmetry of x of h of k, or the coefficient of the filters, we can rewrite this summation to get this expression that we have here. And this is when n is odd. And when n is even, we can write y of n as equal to the summation from k equals 0 to n over 2 minus 1 h of k multiplied by x of n minus k plus x of n minus 1 plus k.
Question.
Mhm.
Is for the first one, is the h of n minus 1 over 2 x n minus 1 over 2, is that part of the summation?
No. This is the element that's going to be in the middle. So that's because n is odd.
Got it, so like that's outside the summation.
Yeah. So n is odd. There is term in the middle. There is this. These two and these two are combined, and that is the term that stays in the middle. So, for instance, if n is 7, then 7 minus 1 over 2 is 3. The fourth element is going to be that element there. Okay. So let's look at the structure for the case when n is odd. And I'll let you do it as a homework when n is even. Okay. Gonna have a delay. We're gonna have another delay. We're gonna continue. Then we're gonna have a delay. Then we're gonna have a delay. Okay. This is x of n minus 1, x of n minus 2, all the way to x of n minus 3 over 2. This is x of n minus 1 over 2. And this one here is x of n minus 1. So now what we're going to do is we're going to take these terms and we're going to add them together. We're going to add this term. 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 Okay. Then we're going to use another color. We're going to take this term, we're going to multiply it by h of 0. We're going to take this term, multiply it by h of 1, and so on. And then Okay, we're going to add all these terms together, and that will give us y of n. Okay. So what is it we accomplished with the filter when there is asymmetry? Linear phase. And what did we get out of in the filter realization? We used as half as many taps, has as many delays as the filter order. Make sense? Because there is the symmetry, and therefore we're having as many, 1/2 as many taps due to symmetry.
So I'm just a little bit confused how that second delay,
Hmm.
that one on the left bottom, how that's connected to the X event.
Oh. So this path continues all the way to this point.
Okay.
So this continues. So x of n keeps getting delayed, more delayed. So again, you can see it from here. Because we have the symmetry, we're going to have the summation to almost half the original summation. Okay. And also, if n is odd, we're going to have n plus 1 over 2 multiplications. And if n is even, we're going to have n over 2 multiplications. Together? Again, you see here the tabs or the filter coefficient h0, h1. We only go to h of n minus 1 over 2. I mean, it's clear because multiplying by x of 0 and multiplying by x of n minus 1, both of these are going to multiply by h of 0. Because h of 0 is going to equal the last tab. Make sense? Okay. So let's wrap up the discussion of the filter realization and then do an example that shows the impact of the quantization on the filter realization. So as a summary, if we have an infinite precision arithmetic, then the filter or the structure has no impact on the results of the filter. However, the structure is important in the following cases. First, when the coefficients are quantized, both the A's and B's are stored using n-bit binary number. Also, when there is input quantization, and when there is a multiplication round off. And we have to do rounding as a result of multiplications. So in this case, the parallel and the cascade perform better in general than direct form. Okay, so to illustrate that, let's look at an example and compare the performance of the two different formats of a filter. Okay, so what we're going to look at is the effect of quantization in the representation of coefficients of the filter. Effect of inaccuracy in representation of the filter. Okay, so now we're going to consider the quantization error. So let's look at this example. So let's say we have a filter that is given by the following: 5/2 z squared plus 2 multiplied by z divided by 99/64 z squared plus 5/2 multiplied by z plus 1. So we look at this filter. We need to make sure the filter is stable. How do we make sure the filter is stable? Anybody remembers?
The table.
Well, like, what is the condition for the stability of a filter?
Jury's test.
Juries to find, okay, but what is the condition? Excellent. The condition. I mean, these filters are causal.
So if the unit circle, like the
All the poles have to be inside the unit circle. All the poles has to be inside the unit circle. Remember that?
Yeah.
Anybody?
I remember that.
Okay.
It's been a long semester.
I know. At least you acknowledge seeing it this semester. Other people might say, you know, never heard of it. Okay. If you look at the poles of this filter, they're at 0.727, 0.888. They're inside the unit circle. Therefore, this filter is stable. Good? Now we're going to go and try to implement this filter. We have a machine that has a finite number of bits to represent the data. So we're going to go to the data the numbers that we have, 5/2. We're going to convert them to a binary, 2, convert to a binary, 99/64, 1. So these are all the coefficients. So this is going to be 0, 1, 0.1, Therefore, we have one fraction bit. 2 is going to be 0, 1, 0.0. 99 over 64, which is going to equal to 1.546. Can't tell if it's a 9 or a 4 here. Nevertheless, is going to equal to 001.100011. And then we have a 1, which we represent as 0, 0, 1.0.
Should 5 be 101?
5 over 2.
Oh.
2.5. So this is a 2 and this is 0.5. 2, 1, and this is the 0.546. This is 1. Okay. So let's say we want to implement this using a system that supports only 3 fractional bits. Or less. What's going to happen? We're going to only keep 3 of the fractions. Here we needed 6 bits to represent fraction bits. So if we're going to implement using only 3 fractional bits, this one is not going to be impacted, this is not going to be impacted, this one is going to be impacted, this is not going to be impacted. What's going to happen to the 99 over 64? Is going to get rounded. So 99 over 64 is going to be represented as 001.100. Now this 001.100 is equal to a 3 over 2. This is 1.5. So we rounded the 1.5469 with 1.5. Okay, great, 1.5. So we're going to come to our filter that we're trying to implement. All of a sudden, it is equal 5 over 2 z squared plus 2 divided by, instead of 99 over 64, now it's 32 z squared plus 5 over 2 z plus 1, which is going to equal to 5 over, which is going to equal to 5 over 2, or 5 over 3 z squared plus 1 over 3 divided by z plus 1 multiplied by z plus 2 over 3.
Sorry, but wasn't there an additional z in the numerator?
Uh,
2z?
There is an additional z. And here is an additional z. Okay. What happened here?
Times it by 2/3.
All of a sudden, we have the poles are at z equal to -1 and -2 over 3. -2 over 3 is fine, but this pole is on the unit circle, which means the system is unstable. Okay. So therefore, if we have the coefficients, shows that we have a pole that is very close to the unit circle. Because of the rounding, apparently we made the pole jump to the unit circle or go outside the unit circle and cause the system to become unstable. Now let's see what happens if we implemented this filter using the cascade form. I know we're running out of time, but just bear with me so we can start the new topic on Wednesday. Okay. So if we implement the filter h of z, 5 over 2 z squared plus 2 multiplied by z divided by 99 over 64 z squared plus 5 over 2z plus 1. If we have it in cascade form, I can write this as h of z equal to 5 over 2 z plus 2 divided by 11 over 8 multiplied by z plus 1 multiplied by z divided by 9 over 8 multiplied by z plus 1. Again, just taking these two, multiplying together, we're going to get the original transfer function. However, if I look at the coefficients here, I have a 5 over 2, I have a 2, I have an 11 over 8, and I have a 9 over 8. And therefore, if I look at the binary representation of these, I'm going to get 0, 1, 0.1. Therefore, I need one fraction. And the 2 is going to be 0, 1, 0, dot 0, 0 fraction, 11 over 8. I can write it as 0, 0, 1, 1, 0, 1, 1. I need 3 fraction bits. And 9 over 8 is going to equal 0, 0, 1, 1, 0, 0, 1. I need 3 fraction bits. So therefore, if I look at this implementation using a cascade, there is no coefficient quantization error. Is that clear? Does that make sense? Does anybody know what the logic behind all this?
So the number of fraction bits used to implement, is that something that will be given normally? Or
I mean, it is really depends on the system you're implementing on. I mean, if you have a microcontroller that has a certain number of bits, I mean, that's what all the numbers are going to be rounded to. Does that make sense? But I mean, you see what happens here. Because I took these coefficients, and these coefficients are the result of multiplication. So this coefficient, I factored it as 2 terms, isn't it? Yeah. So what happens if I want to represent 0.25? This is 0.01. I need 2 bits to represent 0.25. But if I take that 0.25 and say this is equal to 0.5 multiplied by 0.5, then I just need 1 bit to represent it multiplied by 1 bit. Does that make sense? So breaking the fraction into 2 numbers will enable you to accommodate more of the bits to represent each one of these numbers. Sounds good?
Sure, but in the implementation detail of it, all those roundings and all those additions, you're going to start to fail. The more ladder, the more order you have, the higher it's going to start to compound the error, right?
I mean, there are multiple errors that will be in the system. The rounding, I mean, this quantization is going to come from each one of these numbers. Does that make sense? There's other errors that's going to result from the result of this multiplied by this. But at least, I mean, as we've seen,
the beginning will be good.
yes, the system is stable. I mean, and again, this is the example just to illustrate that 2 implementation might look identical on paper, both have the same transfer function, but you add 1 factor to it, which is, for instance, the quantization and the rounding, and all of a sudden you see there's different performance between the 2. Sounds good? Now, if you have time, which most likely we will not have time, we can come back and look at the errors in the filters that comes from quantization and from rounding, and look at their performance. And if you don't, I can just have I have a handout, and you guys can read it if you like. So we'll see after we cover the frequency response how that goes. Thank you, everybody. Thank you, Fort Walton.